Hi, this is Larry Watlington of Keep Cyber Simple. Today we're going to go through what I call data storage fundamentals. I tell you guys, data storage is probably one of the most um, key areas of everything we do with respect to networking and cybersecurity. So how do we store our data, recover data, and keep our data safe? Now, if you want a great a career path, I am telling you this is one way to go, especially if you are a kind of a techie guy and you really want to get into the background of data networking and information systems. However, you got to be good at what you do. Okay, let's get into this. All right, when we think about data storage, we store data on what? Media. Some type of media is used to store data. It could be optical disc, CDs, DVDs, Blu-ray. You don't see a lot of these anymore, but they're still around. Also, our disk drives, and then we still have a lot of magnetic disk drives that still spin. But we also are moving more and more to flash, with the advent of a lot of the technologies out there. Now we're using different types of M2 drives and SSD solid state drive devices. And believe it or not, there is still a market out there for magnetic tape. Why? Because it is a low cost excuse me, solution for long-term data storage. So there's still a marketplace, really, again, for all of these different types of data storage and storage media devices. Now, not understanding the media is one thing, but really also being aware of the different file types, for your file system types. Now, a file system is what an operating system uses to operate the disk, as well as it knows how to store data and retrieve data from whatever type of media that is put on. One of the types that you see quite a bit, especially when you're putting things on flash drives and memory cards and portable devices, is FAT. You may see it now as exFAT, FAT, file allocation table. Like I say, it works great for portable, removable media. So if you have a thumb drive, if you ever look at it, it is typically formatted in a FAT, file allocation table type of format. If you live in the Unix or the Linux world, or even if you got a Mac, if you're a Mac guy, you are operating now with some type of UFS, a Unix file system. You'll see different variants of this UFS, but they all basically work the same. These are what we call a hierarchical file system, where it starts at the base or the root, which is a slash, and then all the other directories span down from that. In this type of file system, everything is a file. What do you mean? Everything is a file. Doesn't matter if it's a hard drive, external media. It looks at everything as a file, and it has to mount those. And here's what I mean. If you ever worked in a Windows environment, if you look at the File Explorer, right, you see you have a C drive and maybe a D drive, or if you plug something in, it pops up as, it names it as its own drive. In the Linux environment or the Mac environment, you don't see those. Why? Because those drives are mounted as a file, as a device, and it sees it as a file. So now, in the Windows environment, the Windows world now really uses NTFS. It used to have DOS, MS-DOS. This is back in the old days. I'm dating myself. Those are some of the legacy Windows operating disk operating systems. Now, like I say, a lot of things now is provided in this NTFS environment, and actually that Windows have also updated from that as well with newer file systems, but it's still based on the same NTFS types of technology. But within that environment, it provides compression, it does encryption, shadowing, copies, shadow services. All these things are done within that environment. Now, for the guys if you are familiar with VMware, like I say, that does your virtualization. I think we've talked about this in some other training classes. It has its own file system, VMFS, your virtual machine file system, and that file system is built specifically for VMware so that it can do what we call snapshots and do disk images, and you're able to export and import those files or using tools like vMotion, and you can move files from one location to another, or from one virtual machine to another virtual machine, and do many things like that. Now, in the network world, like I said, when you're talking about network file systems, it has its own thing, NFS, like I say, network file system, that's specifically used to share files across a network. Okay, very important to understand this, because when you're working in a networked environment, you may have Windows machines, you may have Linux machines, you may have Macs, all those machines on the network, and you want to be able to share files across machines that have different file types. So having a network file system is very important, very critical from that perspective. Now, so understanding file system types, trust me, this could be a whole class within itself to break each of these down, but we're not going to do that here. Just realize that these types of file systems exist. Excuse me. So how does a client access storage? Well, three basic ways, okay, at the fundamental level. All right, first, one we're going to talk about is what I call direct attached storage, or DAS, okay? That's your basic computer, okay? If you look at your basic computer where you got application, you got a file system, and then you have a hard drive. It could be it could be a SDD, it could be, regular hard drive, spinning drive, but that is directly attached to your computing environment. Directly attached. And like I said, it has what we call block level requests, where it goes and grabs blocks of data and brings them back and forth. So that's your basic computer, your basic home computer. For most of us, that's what we have. We have a hard drive that's actually installed in that system, directly attached. Now, also, you can have that external. For instance, you could have an external piece of media that's plugged in via USB, right? Still direct attached. Next type we talk about is network attached storage, or NAS. Okay, now what we have here, same thing, you have your computing environment, right? You got your computing environment. But now, instead of having the storage device directly connected, we have a network, like a storage network that actually connects to that system. This is just kind of a snapshot of what that could look like. You've probably seen some of these devices. I've got a couple of them sitting behind mine, TNAP devices. Can hold multiple drives, and they're all connected on the same network. All my computers, they're network attached, okay? Now, the third type, and this is when you start getting into data centers and large applications, what we call a storage attached network. You may go, wait a minute, this is getting confusing. We got NAS, we got SAN, we got DAS. Don't get confused with the terminology, because I know it starts sounding the same. That's why I want to kind of break these down for you. So in this environment, now, you see something happens a little differently in this environment. We have our computing environment where we have our applications, but the file system is no longer part of the computing environment. Now we have a storage network, and we're doing file level requests from a storage system. Now, this storage system could be in the data center. It could be in a facility, thousands of miles, across the world. But this is where we have really large things like NetApps. I don't know if you're familiar with the term NetApp. This is a company and that's what they really specialize in, is making large-scale storage devices for data centers, for large data centers. Again, directly attached is connected to your computer. Network attached is connected to the network that you're on. Storage attached network, where it is a separate network. And like I say, we'll talk about this a little bit more. Again, when we talk direct attach, that's that hard drive that's sitting in your computer. Also, it could be a box that's external, okay, that you have multiple computers, but still it's directly attached via some type of cable, typically like a USB or a Thunderbolt cable. Now, why do we need, when we think about this NAS, get a little bit deeper, like I said, what this really allows is file sharing across the network. So hopefully this explains it a little bit better. And this is probably very similar to your home network. This could be wired, or it could also be wireless, because a lot of these network devices, they do have a wireless card interface, so it could be wireless. But let's say this is your home or small office network, where you have a LAN, you got a router or a switch with a LAN. You've got your devices connected to that. You got your computers. You may have a printer. You may have an application server, your email server, or your SharePoint server, whatever it may be. They're all connected to the same local area network, and your storage device again is connected to that same network. Great part about this, because this could be a Windows machine, this could be a Linux Ubuntu machine, and this could be a Mac, all on sharing the same network across internet or IP-based system. And they all can share the same file system. And the great thing also about this, again, if this is wireless, I can have my mobile device, my phone or tablet, and I could also push files, store files off of my mobile device onto here. So like I say, that's a direct attached network attached storage. Now, what a storage area network looks like is, again, where I've got my network, right? I have all my clients. Again, these could be Windows or Linux or Red Hat, whatever it may be. Now, this is the rest of my network. From here over, looked very similar to what we just talked about. However, on the back end of this, now I've got, this could be fiber channel, it could be ISCA, it could be a lot of different protocols we use to be able to now connect to the back end storage application. So you see, the storage is its own separate network. Its own separate network, separate from the IP network that we use day to day with that interfaces with our applications. All right, let's take a look at how storage has evolved, the architecture over the last 2 years. You know, when we, really the environment we worked in for a long time was what I'll call a server-centric storage architecture. What do I mean by that? Let's say in a small company, right? You have an email, you got printers, and you got SharePoint running. Well, you got servers for each one of those. You have an email server, and that email server has its own, has its own storage. It could have its own drives in that server, right? Or it could have its own network attached devices. Your print server, same thing. It's got its own storage in here. Your SharePoint server could have its own storage. Well, that's all well and good, right? Well, the problem you run into with this, I will probably guarantee in most organizations, your SharePoint server is running, is using a lot more storage resources than your print server. So this guy over here is probably full. It's probably, they're backing it up and trying to remove files off of it daily. Whereas this print server is probably underutilized. So there's probably a lot of storage capacity on that print server that's never getting used. However, so now as a company, I go to my boss and say, look, we've got to spend more money to get more storage for our SharePoint. And a good CISO is going to go, well, look, we spent X amount of dollars on all this infrastructure. Why do we need more? Because he's probably realizing that, some of these other servers over here are probably underutilized. That is what drove us to a different way of thinking about storage, to what we call information-centric storage architecture. So let's say I've got my same email, printer, SharePoint server. However, instead of using that storage in these devices, now I've pushed it across some type of a storage network, and now I can share all of these storage resources, all of these drives now. So now I can actually now do different types of configurations to where whichever server needs storage, it all saves it into this pool. So I can pool my storage together and become much more efficient and effective with my storage resources. So server-centric, information-centric. All right? Now, when we talk about storage, one thing that I always have to cover, and I know this gets confusing sometimes, is RAIDs, okay? Redundant Array of Independent Drives, RAIDs. Because we get into the ones, the zeros, the fives, the 6, 10, I don't know. I get so confused. Well, we're going to walk through these, break it down so that hopefully you get a little better understanding of what these different types of RAIDs are. And all these are, again, it's a technique that is able to combine multiple disk drives into one logical unit. Okay, and when you talk RAID, you may hear this term, a LUN, a logical unit number. Whereas this, okay, so even though I may have 5 drives, right? 5 separate hard drives. What the RAID controller does, it presents those in some other logical fashion to where I can combine them all together to where they would logically look like one drive to my computer. For instance, I will guarantee that if you're on where you work, if you're on a network and what you are calling maybe your Z drive or your X drive or your S drive, which is the shared drive, to your computer, it looks like one drive, S drive. Guarantee you there are probably multiple actual physical disks that are built together to represent that one drive. So that's what a RAID does. Now, when we talk about RAIDs, we have to think about 2 things. The different methods of data storage. One is a file level storage. Okay, file level storage, like I say, it's most commonly used for storage systems for NASes and other network file systems. And when I'm talking about file level storage, what we're doing now, we are storing things based on a set of files. So, and that way it's saved to media as a file, and we can recover it or restore it or retrieve it as a file. Like I said, it's the most inexpensive, simple, easy to implement. Second type is what we call block level storage. Now, with block level storage, like I said, that's just raw volumes of storage is created, and each block can be controlled as an individual hard drive. Okay? So instead of being able to write as files, it is just saying, okay, here is a raw amount of storage, and now we can break that up into whatever set of blocks we want to. Like I said, we use these again large on your storage area networks, in the virtual environment, and but it is more expensive and it's more complicated. But it does make transporting the data much more efficient and much more reliable when we operate in that block environment. Reason this is important because as you look at NAS and at RAIDs, there are some where we can operate from a file level system or from a block level. All right, let's talk about some of the RAID techniques. There's 2 basic techniques that we're going to talk about. One is called stripping. Okay, and stripping, very simple. And again, it's operating kind of at file level. So here's my host computer. Okay, I got a file. The RAID controller, what the RAID controller does, it breaks that file up across all 3 of these drives. Okay, now all 3 of these drives together is called a stripe. All right, so I've got three drives. The RAID controller saves this one file on my computer, breaks it up, and saves it across all 3 of those. Again, easy, fast, and just a quick way of backing things up. Second method is called mirroring. Okay, when I mirror, now I'm writing in a block format. Okay, so now I'm going to write, excuse me, what the RAID controller does, it's going to mirror what's on this disk with what's on that set of the disk. Now you see the advantages, disadvantages. Here, I've got redundancy. So if something fails, I've got my data is automatically mirrored. But it's writing twice, so it's not as efficient. In this world, it writes really quickly, but if disk fails, I've lost my files. Now, using this, like I say, and there's a third technique that we are going to talk about. It's called parity. I'm going to get into that a little bit later. But now this is where you get all those different types of RAID configurations. RAID 0, 1, a 1 plus 0. So we call a RAID 10, 3, 5, and 6. Okay, and we're going to walk through each of these in the next set of slides. So we're not going to spend time right here because we're going to walk through each of these. So let's take a look at RAID 0. And this really breaks down the striping a little bit more. Like I said, the thing with a RAID 0, let's say each of these is data that's coming from a host computer. This is file A, data set B, data set C. The RAID controller in a stripped environment, and I've got 4 data disks, four hard drives that I'm using in my RAID device. So when A comes in, what does it do? Yeah, It breaks it up across all four drives: A1, A2, A3, A4. B comes in, does the same thing: B1, B2, B3, B4. C comes in, does the same thing. So you see all three of my files, all that data was written across all four of those drives. Now, what does it do? What benefits does it give me? If you look up in the corner, it says what? It gives me high data throughput, meaning I can write this really quickly to these drives, and I can save and retrieve my data really quickly off of this system. However, no fault tolerance. What do we mean by fault tolerance? Is that if any one of these arrays, any one of these data disks fail, I've lost all my data, because a part of all the data is on all of these disks. So I've lost A, I've lost file B, I've lost file C. So that is the drawback. Well, mirroring, again, does something a little different. Again, so here's my data set. Data is coming from my computer, right? The RAID controller, what it does, it sets it up, takes those same four drives, and it puts them in pairs. So here's a mirrored set. Here's a mirrored set, okay? So now when A comes in, it's going to write A here, and it's going to write it also here. So it mirrors. Same thing with B. Same thing with C. And as data comes in, it's going to continue to write D and E and F. So you see everything is mirrored. So if this drive fails, I can still recover my data for D, E, and F. Or if this drive fails, I can still recover my data off of for A, B, and C off the other drives. Now, that gives me 100% redundancy, right? 100% redundancy. However, it's slow. Why? Because everything has to be written twice. And other thing, it reduces my storage capacity. Because now, even though I got 4 drives, I've cut my capacity in half. Because 2 of the drives are used to mirror or duplicate what's on the other 2 drives. So I only have 50% capacity of those 4 drives, okay? But I do have redundancy, so it depends on what your objectives are. If you need to be sure that your data is backed up and is available, higher availability, then you may want some type of mirroring. If you just need to be sure that your data is saved and you need to write and get to it quickly, because some things don't last long enough, like in some types of databases. Data is written over, and it is so non-persistent to having replicated data may not be important. But having the speed to get to it and recall it and save it really quick, that is sometimes maybe more important than mirroring. Okay, but let's say, how can we bring this together and get maybe the best of both worlds? Well, that's what we call a nested RAID. And a nested RAID, that's a combination of a RAID 1 mirroring and a RAID 0, which is the striping. So what I say? So we look at this. It comes in. We're gonna do the stripping first, and then we're gonna mirror. So what we get, if you look here, we still got the same 2 mirrored sets, but data A1 is written here, and it's also stripped. It's broken up and stripped across the second mirrored set. So I have A1 and A1, A2 and A2, B1, B1, B2, B2. So it provides me some fault tolerance, however, but it also speeds up my writing capability, because it's writing smaller chunks. It's only writing a portion here and a portion there. So if this drive fails, I still got redundancy of A2, and I also still have A1 and A1. So now it speeds up the performance because I have less amount written to each drive. But it also provides me the redundancy. Again, what do I lose though? Capacity. It still requires twice as many disks, or 50% of utilization of these four disks. Now I can do the same thing if I reverse that and call it the 0-1. Now typically you don't really see this one that much. You see the RAID 10s more. So this, what I'm going to do, I'm going to mirror first, then do my stripping. Okay. So the mirroring, where I'm going to have A1 and A2 mirrored, A1, A2. So you see the difference. Before I had A1 and A1 on a set, A2, A2 on a set. Now I have A1 and A2 mirrored and stripped here, A1, A2 here. Basically the same results, from both. It speeds up performance and provides some level of redundancy, but you're going to lose space or capacity. Okay, this is what we're going to talk about is parity. All right, with parity. Parity is basically it's like a checksum, and what that checksum does, it adds up all the data that's on the drives, and it knows not so much how it doesn't mirror all the data, but it knows the value of the data that should be on each drive, so that if something happens, it can rebuild that drive. So what do I mean by that? So it looks very similar, right, to what we saw before with stripping, where it comes in A1, A2, A3, A4, B1, B2, B3, B4, all the way down, right, and on our drives, on our data drives. Now, I have it to do this type of parity. I've got another drive, a dedicated parity disk. And on that dedicated parity disk is where these checksum is held. And what that checksum is for each one. So what it does, it looks at all the data that's on that of A, and it has the parities for A. So let's say if a drive failed, it is able to calculate what should have been on that drive and recreate it. Okay, so with that is a way of doing parity. Now, what's the good thing about that? Like I say, it's redundant. Gives you good high throughput. Like I said, it's good for things like video streaming and things like that, where you're doing real time. However, a little expensive. Why? Because now I have to buy another set of disk, and the sole purpose of that disk is just to hold parity. So my efficiency or effectiveness kind of drops a little bit because it's gotten a little expensive on me. What we can do now, a RAID 5, and actually I use this one in my home setup as a RAID 5. This is distributed parity. It's basically the same concept. However, instead of having a dedicated parity disk, now I write parity is distributed across all the other disks. Here's what I mean by that. So if I look now, I take my 5 drives that I already had, and I had 4 and I used 1 for dedicated parity. But I will guarantee you that dedicated parity disk is not close to being full, because the parity is just not that much data. So now I can write my A1, A2, A3, A4, and on this drive I put my parity for A. On my next setup, I write B1, B2, B3, but instead of putting it all on a dedicated, I'm going to put the parity on drive 4. So I can still write some data, B4, on this drive that before was dedicated. The same thing with C. So I've distributed the parity across all the drives, but now it allows me to be a little more efficient or effective with resources. But it does slow down and reduce performance because now that parity has been distributed across all those drives. Now, RAID 6, basically the same thing, but what it does now is dual parity. Okay, single parity, if one drive fails, if one array fails, it can recover it. If 2 drives fail, it is unable. Dual parity will allow you to be able to now recover data if 2 arrays fail. Okay, again, great for data redundancy, but what it does, it slows down the write time. So if you've got applications where you need to be able to write quickly, this is not a good solution, because now because all this, calculating that parity takes time, and every time something changes, the parity has to be recalculated. So if you think about just the mathematics behind this, it takes time to develop that parity. So if you're doing a lot of writing, a lot of changing and updating to your disk, your parity is constantly changing. Every time a bit changes on any of these drives, the parity has to be recalculated. So now you see how that can become, from a performance perspective, can decrease performance with respect to writing data onto the drive. So you're probably wondering, how does this parity thing work? Let's talk about that, especially from a data, excuse me, recovery perspective. Okay, in this example, I'm not going to use binary because it would just make the math very difficult. So I'm using decimal numbers just for an example. Okay, just for the sake of teaching. All right, so I've got a setup here, right? Where I've got a host, RAID controller, and I have 5 drives. 4 of these are data drives. 1 is the parity. So what I've got here is just on each drive is a number of, I'm just call them files that were saved to these drives. Drive 1, 4. Drive 2, D2 has 6 files. D3 has 1 file. D4 has 7 files. So what the parity does, it does the math and adds 4, 6, 1, and 7, and it says, hey, there's 18. That's the right number, 18. All right, boom. Disk 3 just failed, crash. So now we have an unknown. I know this takes you back to 9th grade algebra, right? Solving for an unknown. But really, that's all the parity disk is really doing. So now, what do we know? We still have 4 on disk 1, 6 on disk 2. We don't know what's on disk 3, and 7, disk 8, and we know what the answer should be. So now we just do regular mathematics to solve for an unknown. 4 plus 6 plus x plus 7 equals 18. That's what we know. So now we just kind of flip that around. You remember the distributive properties, right? All that from, ooh, you're like, man, I didn't think I'd ever use this stuff from high school again. Guess what? You are. So now we get x on the other side of the equation. X equals 18 minus 4 minus 6 minus 7. So if you do that math, then x is equal to 1. So now the RAID controller is able to rebuild that file set because it knows that one file should be on disk 3. So when I replace disk 3, the RAID controller is able to put the correct information back onto that disk. That's basically what the parity is doing in a very simple, simplistic definition. Trust me, there's a lot more moving pieces there when you, when you look at it from a binary or from a ones and zeros perspective. So a real quick snapshot. That's just the overall RAID comparisons. These are your RAID types, your RAID levels, 0 all the way through a 6. And now you can start to see, how many disks are required. Minimum amount of disks. So for a RAID 0, you're going to need at least 1 disk. For a RAID 1, you're going to need at least 2 disks to be able to mirror. For a RAID 10 or RAID 01, the nested, you're going to need at least 4 disks, 4 drives. If you want to do a RAID 3, you're going to need 3 disks. A RAID 5 is going to need 3 disks. RAID 6, you're going to need a minimum of 4 disks. So it gives you an idea. And also it tells you how much space, okay? The actual usable storage space. For RAID 1, you got 1 disk and you use 100% of it. For RAID 2, you're going to have 2 disks, so you're only using 50%. You're not, let's say if these were all, 10, excuse me, 1 terabyte hard drives. Well, I got 2 1 terabyte hard drives. However, the amount of data I'm going to save is going to be 1 terabyte, not 2 terabyte. The same thing all the way down. Read performance, your write performance. Write penalty meaning that how much it's going to slow you down, how much you're going to lose every time you write. And protection, how is it protected? There's no protection with the RAID 0, RAID 1, and a RAID 10. It's mirrored, and the other 3, as you see, is parity. So there's benefits, there's trade-offs. Let's put it that way. Trade-offs to any type of RAID that you use. So as you're setting up your RAIDs, be aware of that. Now, the key thing about storing data isn't just that you stored it, but you need to be able to recover it. So when we think about data backup and recovery, this is critical, especially from the incident response, disaster preparedness. You have to understand this side of data, how to back it up, what format is it backed up in, and how do I recover it? How do I get to that? So and there's methods and techniques to this. So one way we can do is a full backup. Let's say every week, on Sunday, we just want to back our data up. Okay, very simplistic. It works. However, let's say if something happened between Sunday to Sunday and I need to recover that data. Well, you see, it could be very easily. I'm creating data during the week, and if I just back up here, is I could lose data that I've created from one week if I'm just doing a 7 day, excuse me, a 7 day backup. But you can do it that way. All right, another way to do it though is do what we call incremental backups. Now, incremental backups helps you with that. So, what I can do now Monday, I save my data. Then Tuesday, I save and back up whatever I made Tuesday, Wednesday, Thursday, all the way to Friday. And then on Sunday, I do a full backup again. So now I've incrementally saved new data during the week or data that has changed during the week and do a backup. And I can do this every week, and then I have a full backup. Or I can do what we call a differential backup. Okay, and this is like a cumulative backup. So now what I'm doing, I create data on Monday and I back it up. I create data on Tuesday. Well, what I'm going to do, I'm going to back up my Monday and Tuesday data. And Wednesday, I'm going to back up Monday, Tuesday, Wednesday, Thursday, Monday, Tuesday, Wednesday, Thursday. And as you see, incrementally, it just continues to grow until I get to Saturday. I've got all my data backed up except what I may create on Saturday night. And then Sunday, I do a full backup again. So incremental backups, differential backups, full backups. Another way to look at this is now from a restore perspective. So let's say that, for an incremental backup, like we talked about, let's say Monday, I do a full backup on Monday. I got 3 files, full backup, good to go. Well, Tuesday comes along and I create another document. All right, well, you know what? I'm going to back that up too. Then Wednesday comes along, I updated file 3. You see, file 3 over here changed. So now I got to back up the updates to the changes to file 3. Thursday, I create another file. So how would I have to back it up? Well, as you see, I would have to back up each one of those incrementally. My full backup from Monday, the first 3 files, I'm back. And if I want to recover these, back to the production environment, I would have to recover all 4 of those days, Monday, Tuesday, Wednesday, and Thursday, because Friday, I'm going to have all the files, to have all the files available on Friday. So what does this provide me? Well, one thing, it's quicker, it's faster, it takes less time to back up in this method. Why? Because all I'm backing up is the incremental differences that have changed. It's just those changes. So the speed is quick because typically those are smaller file sizes. However, on the flip side of that, it's longer restore time. Why? Because for me to restore these, I got to restore each one of these separate. I got to restore this one, this one, this one, this one, and this one. So restoral is going to take longer. Why is this important? Well, when you get into understanding incident response and you start talking about 2 important factors within incident response called RTO and RPO, recovery time objective and recovery point objectives. That will drive how you're going to do your backups, okay? Because recovery time objectives means how far back do I need to save data? Recovery point, at what point if I don't recover fast enough that I'm out of business. So now restoral time may be more important than the time it takes to back up. If your data doesn't change a lot, then having to take more or less time to back it up may not be an issue. But if you need to get that data really quickly after an emergency or after an incident, then the recovery time may be more important. So incremental backups, that's what it looks like. Let's look at the same thing from a differential backup perspective. Okay, so Monday, like I said, I do a full backup on Monday. I backed up files 1, 2, and 3. Then Tuesday comes along. Now I'm going to back up file 4. Wednesday, I'm going to back up file 4 and 5 because I've already done a full backup here. So now I'm cumulatively backing each one of these up. And now Thursday, I'm backing up file 4, 5, and 6. So now when I get to want to recover those, I just have to recover 2 things. My Monday full backup and my Thursday cumulative backup, so that by Friday I've got all the files and all my data is there. Again, What is this going to take? Well, it's going to take more time to back up and requires more storage space. Why? Because I'm backing up more files. I'm not just backing up the incremental changes, but when I back up on Thursday, I'm replicating these what I've already backed up. So my Thursday is going to take a long time, and it's going to require more storage. Why? Because I'm backing up things cumulatively. However, my restore time is much quicker. Why? Because I already have these pools that now all I have to do back up is Monday and Thursday, and I'm back in business. So why is all this important? From a technical perspective, it's great to know. But really, this is about business. This is about availability. And any one of us who's been in cybersecurity, we know the three-legged stool, or our triad: confidentiality, integrity, and availability. Now we are talking things that are key to availability, okay? So having a backup plan isn't just something that our IT guys do or cyber. This is something that you want to work with your organizational leadership, because the data you're backing up is company data, it's business data. So they're the ones who really should help you establish what the cadence, what the tempo of backing up data looks like. One way to present that to leadership is in a tiered approach. Okay, here's what I mean. A tiered approach to data. Forget backing up for a second. Understand how important data is, how quickly do people need it, and what's the value of that data. That will drive your data strategy of how best to back it up, okay? So let's look at data. Let's look at data from a tier perspective. Tier 1, that's cool. We're going to call it Tier 1 data. That is your mission critical data that's got to be accessed, got to be secured, and that's the one that you want to ensure that you got the right type of RAID setup or whatever it may be, because this is the secret sauce data. So you want to be sure it's secured, and if you need to recover it, you need to get to it quickly. So this is where you want to start spending your dollars at, or allocating resources to. Tier 2 data. That's the data such as your email or your enterprise resource planning type of data. It runs your business. It's not the secret sauce of your business, but it's what runs the business. Now that's, like I say, that's where you start balancing cost and performance. So that type of data, do you really need it? Maybe on a RAID 6, maybe not. But you want it where you can get to it and available. Tier 3 data, that's things like your finance data. Stuff that needs to be kept but doesn't have to be accessed all the time. So now I don't have to store that. I don't, in the same fashion as I do my Tier 1 and Tier 2 data. Okay, so now when we start talking about read and write times and things like that, now you start seeing where it becomes important, because if I say financial records, like for tax purposes, I may not only need to get to that just like you do at home. You pull your tax data out pretty much once a year. You gather all your tax stuff. Businesses are the same way. So it's not something I'm going to need to read and write to constantly. So and then Tier 4 data, like I say, that's data that's required, let's say, for compliance, your audit logs. You need that stuff, but need to keep them for years and years. So now that changes how you're going to do that. Am I going to put this on a high-speed RAID? Probably not. But am I going to maybe put it on magnetic tape, or where I can assess it and store large amounts, over a long period of time and be able to pull it back up? So understanding what your data in your organization looks like is premium, is paramount to how you set up and establish your data storage environment. All right, guys. So we've covered a lot. We've covered a lot of things today, right? With respect to data storage, data fundamentals. Hope this helps. Like I say, this video went a little longer than my usual ones. I usually try to cut them off at 30 minutes, but I wanted to keep going. I hope this helps, and we will see you in the next lesson.